Yesterday, we talked about the earthquake. Today, we need to talk about what it woke up. Because 2 days ago, on January 15th, 2026, when that magnitude 6.0 quake tore through the Blanco Fracture Zone, seismologists didn't just record an earthquake, they watched something 300 miles away respond. Axial Seamount, the most monitored underwater volcano on Earth, has been inflating for years, swelling like a balloon filled with molten rock. Scientists had models, predictions, timelines. Then the quake hit, and those models started unraveling. Tonight, we're diving beneath 4,500 feet of Pacific water to understand what's really happening down there. Stay with me until the end, because what they've discovered about the connection between that earthquake and this volcano might change everything we thought we knew about the Pacific Northwest. And it's genuinely terrifying. Subscribe and follow along as more data from Axial Seamount, the Blanco Fracture Zone, and the broader Pacific Northwest continues streaming in. Because what unfolds over the coming months will either confirm that these signals are just geological noise, or reveal that we've been missing critical connections in how tectonic systems interact beneath the surface. This isn't about predicting the next eruption with certainty. It's about recognizing that the patterns we thought we understood are changing, and understanding why that matters before the next phase of this sequence begins. 2 days ago, while most of us were going about our lives, the ocean floor convulsed. On January 15th, 2026, a magnitude 6.0 earthquake ripped through the Blanco Fracture Zone, a jagged scar in the Earth's crust, sitting 180 miles off the Oregon coast. The tremor registered instantly across seismic networks stretching from California to Alaska, and within minutes, scientists were staring at their screens with a mixture of fascination and something that looked uncomfortably like concern. Officials were quick to reassure the public. No tsunami had been triggered. Coastal communities could breathe easy. But here's what they didn't tell you in those initial press releases. This earthquake arrived at perhaps the worst possible moment in recent geologic history. Because right now, just 300 miles from where that quake struck, something massive is stirring beneath the Pacific Ocean. Something that's been inflating, swelling, building pressure for years. And the timing of this seismic jolt has turned routine monitoring into what one researcher privately called heightened scrutiny. The Blanco Fracture Zone is what geologists call a transform fault, a place where two massive slabs of the Earth's crust grind past each other like tectonic freight trains passing in opposite directions. Most earthquakes here barely make the news. They happen, they're recorded, scientists note them in databases, and life goes on. But this one was different. This one lit up seismometer arrays across the Pacific Northwest like a Christmas tree, sending waveforms of unusual complexity rippling through monitoring stations from the coast to the Cascades. Scientists monitoring these systems didn't just see a simple quake signature. They saw spikes in tremor counts, unusual patterns in the seismic data, frequencies that suggested something more complex than a straightforward fault slip. And almost immediately, researchers began flooding internal messaging channels, cross-referencing this new data with something they've been watching obsessively for months. Because 300 miles to the southwest, beneath 4,500 feet of cold Pacific water, Axial Seamount has been behaving strangely. Axial Seamount is the most active underwater volcano in the entire Northeast Pacific. It sits on the Juan de Fuca Ridge, a massive crack in the ocean floor where new crust is constantly being born. And for the past several years, this volcano has been doing something it's done before. Something scientists have learned to recognize and even predict. It's been inflating. The seafloor above its magma chamber has been rising, swelling upward as molten rock accumulates in the shallow reservoir beneath the summit. Instruments have measured this uplift in real time, watching the volcano literally breathe as it prepares for what many researchers believe is an inevitable eruption. But here's where things get weird, and this is what has volcanologists genuinely puzzled. The inflation that everyone expected to continue steadily toward an eruption threshold has started behaving unpredictably. After approaching levels last seen before the 2015 eruption, the rate of uplift slowed. Then it plateaued. Then it picked up again, but not in the smooth, predictable curve that previous cycles followed. It's like watching a pressure gauge that should be climbing steadily, instead stutter and hesitate, and nobody's entirely sure what that means. The January 15th earthquake at Blanco didn't exceed any catastrophic thresholds. It didn't directly threaten the Cascadia subduction zone, the real monster lurking beneath the Pacific Northwest. It didn't send tsunamis crashing into coastal towns. But it arrived at precisely the moment when scientists were already grappling with unusual signals from Axial, already trying to understand why their models weren't quite matching reality, already wondering if something fundamental about their understanding of this system might be incomplete. Seismologists and volcanologists have been in constant communication since the quake hit. They're comparing notes, overlaying datasets, looking for connections that might not be immediately obvious. Because while most scientists will tell you there's no direct mechanical link between a transform fault earthquake and a submarine volcano 300 miles away, they'll also admit that the Earth's crust is far more interconnected than we once thought. Stress doesn't just build up and release in isolation. It migrates, redistributes, finds pathways through rock and fault systems in ways we're only beginning to understand. The recommendation from monitoring agencies has quietly shifted. What was routine observation has become active vigilance, not panic, not evacuation orders, but a heightened state of attention. Scientists are watching the data feeds more closely, running more frequent analyses, preparing for scenarios they hope won't materialize, but can't afford to ignore. And the question they're all asking, the one that keeps coming up in conference calls and research meetings, is deceptively simple. Was this just geological noise from a tectonically active region? Or are we watching the opening act of something much larger? Because if there's one thing decades of studying the Pacific Northwest have taught us, it's that this region doesn't do anything halfway. When Cascadia moves, it moves catastrophically. When its volcanoes erupt, they reshape coastlines. And when its tectonic plates decide to rearrange themselves, the consequences can echo for generations. So when a significant earthquake strikes just as an underwater volcano shows unusual behavior, just as seismic swarms are trending upward, just as multiple monitoring systems are detecting anomalies they can't quite explain, you pay attention. The data right now tells us several things with confidence. The Blanco quake was substantial, but not extraordinary for that fault system. Axial Seamount continues to inflate, though not according to the script previous eruptions followed. Seismic activity in the region remains elevated, but below crisis thresholds. And most importantly, there's no immediate danger to coastal populations, no reason for alarm or evacuation. But between the lines of those reassurances, there's something else. A sense that we're watching a complex system in transition, moving towards some state we can measure, but not fully predict. What happens next might unfold over months, or it might unfold over years. Axial could erupt tomorrow, or it could continue this strange dance of inflation and pause for another decade. The connection between the Blanco quake and the volcano's behavior might be purely coincidental, or it might hint at stress patterns we don't yet have the instruments to fully map. But one thing is certain. The Pacific Northwest's subterranean machinery is active, restless, and far more complex than anyone imagined even a decade ago. And we're about to dive into exactly why that should matter to anyone who's ever looked at a map of the West Coast and wondered what lies beneath. Axial Seamount doesn't look like much on a map. It's a dot in the Pacific Ocean, a coordinate that means nothing to anyone except the scientists who've made it their life's work. But beneath that cold, dark water, beneath 4,500 feet of ocean that would crush a human body in seconds, there's a mountain. A volcano rising nearly half a mile from the surrounding seafloor, crowned with a summit caldera 2 miles wide and 400 feet deep. and right now that caldera is slowly, measurably rising. The remarkable thing about Axial Seamount isn't just that it erupts regularly. Lots of volcanoes do that. What makes Axial extraordinary is that it erupts predictably, or at least it used to. In 1998, it erupted. Scientists documented the event after the fact, noting changes in the seafloor and disruptions to monitoring equipment. Then in 2011, it erupted again. This time, researchers had better instruments in place, and they watched in real time as seismic activity spiked, the seafloor deformed, and fresh lava poured across the caldera floor. Then in 2015, something remarkable happened. Scientists actually predicted an eruption window based on inflation data, and Axial obliged, erupting almost exactly when the models suggested it would. That 2015 success story made headlines in the volcanology world. For the first time, researchers had successfully forecast a submarine volcanic eruption using physics-based models rather than just watching and waiting. The pattern seemed clear. Magma accumulates in a shallow reservoir beneath the summit. The seafloor bulges upward as pressure builds, and when the uplift reaches a certain threshold, somewhere around 8 to 9 feet of total inflation, the volcano erupts. It deflates dramatically as lava drains from the chamber. Then the cycle begins again. Inflate, erupt, deflate, repeat. Simple, elegant, predictable. Except now it's not. After the 2015 eruption, Axial began inflating again almost immediately, exactly as expected. Instruments on the seafloor measured steady uplift, millimeters and centimeters adding up month by month. By late 2024, the volcano had regained most of the elevation lost during the previous eruption. Scientists started quietly discussing eruption windows, running models, placing bets over beers about whether it would happen in late 2025 or early 2026. Everything seemed to be following the script. Then the script changed. The rate of inflation, which had been climbing steadily, started to slow. Not dramatically, not in a way that suggested the system was shutting down, but noticeably. The smooth upward curve that researchers had been tracking began to flatten, to plateau. By mid-2025, the uplift that everyone expected to continue marching toward that 8 to 9 foot threshold had stalled at around 7 feet. And it just sat there, hovering, occasionally ticking upward a bit, but never quite reaching the levels that previous cycles suggested should trigger an eruption. This is where volcanology gets simultaneously frustrating and fascinating. On paper, magma accumulation should be relatively straightforward. Hot rock rises from depth, fills a chamber, pressure builds, eventually something has to give. But the Earth doesn't read textbooks. The crust above a magma chamber isn't a uniform shell that simply inflates like a balloon. It's fractured, heterogeneous, shot through with faults and weak zones and pathways that can open and close in response to stress. Sometimes magma finds escape routes that instruments can't detect. Sometimes the reservoir geometry changes as the system evolves. Sometimes the laws of physics are operating exactly as expected, but our understanding of the boundary conditions is incomplete. What scientists are seeing at Axial right now is a masterclass in uncertainty. The volcano hasn't stopped inflating entirely. Seismic data shows that magma is still moving beneath the summit. Temperature sensors and chemical sampling from underwater robots detect signs of ongoing volcanic activity. But the relationship between these signals and the ultimate outcome, the timing and magnitude of the next eruption, has become frustratingly opaque. The models that worked so well in 2015 are now hedging their bets, offering eruption windows that stretch from mid-2026 into 2027 or even beyond. This matters because Axial Seamount has become a natural laboratory for testing our understanding of volcanic processes. Unlike most volcanoes, which hide their internal workings beneath miles of solid rock, Axial is wired like a patient in intensive care. The Ocean Observatory's initiative has installed a network of sensors across the caldera floor, connected by fiber optic cables that stream data to shore in real time. Scientists can watch seismic waves propagate through the volcano's interior, measure ground deformation to millimeter precision, detect chemical changes in hydrothermal vent fluids, and observe biological communities responding to volcanic heat. It's the most comprehensively monitored underwater volcano on Earth, and right now it's teaching us that we still have a lot to learn. The puzzle deepens when you look at the seismicity patterns. Sometimes earthquake counts spike without corresponding increases in inflation. Other times, inflation accelerates while seismic activity remains quiet. There's supposed to be a relationship between these signals, a coupling between magma movement and the rock fracturing it causes. But at Axial, that relationship isn't always obvious. It's like watching two dancers who should be moving in sync occasionally step on each other's toes, and volcanologists are trying to figure out if that means the music has changed or if the dancers are improvising. Some researchers have suggested that the magma plumbing system beneath Axial might be more complex than the simple single reservoir model implies. Maybe there are multiple chambers at different depths, feeding into each other in ways that create irregular inflation patterns. Maybe the pathways that connect these chambers occasionally clog or shift, changing how efficiently magma can rise. Maybe the crust itself is evolving, developing new fractures that alter how stress distributes across the summit region. All of these hypotheses are plausible, and all of them make predictions significantly harder. But here's what makes the current situation genuinely interesting. We're watching these processes unfold in real time with better instruments than we've ever had before. Every plateau in the inflation curve, every seismic swarm that doesn't quite match expectations, every anomaly in the data is teaching scientists something about how volcanic systems actually work versus how we think they should work. And what we're learning is that volcanoes, even relatively simple ones like Axial, are complex adaptive systems that don't always follow linear rules. The revised eruption forecast now points to mid to late 2026 as the most probable window, but that estimate comes with massive error bars. It could happen sooner. It could happen later. It could happen in a way that doesn't resemble previous eruptions at all. And that uncertainty isn't a failure of science. It's an honest acknowledgement that we're pushing the boundaries of what's currently predictable given our understanding of volcanic physics and the limitations of our monitoring networks. So, as Axial continues its stuttering inflation, as seismometers record thousands of tiny earthquakes that may or may not mean anything, as scientists around the world analyze data streams and refine their models, one question looms larger than the rest. If we can't perfectly predict when a thoroughly monitored, relatively simple underwater volcano will erupt, what hope do we have of understanding the far more complex tectonic systems that threaten entire coastlines? And what if the inflation patterns we're seeing aren't just about magma at all, but about something larger happening deep beneath the Pacific Northwest? Here's the story we tell ourselves about volcanoes. Magma rises from the mantle, hot and buoyant, forcing its way upward through cracks in the Earth's crust. It accumulates in a chamber, a reservoir of molten rock waiting for the pressure to build high enough to breach whatever barrier keeps it contained. Eventually, inevitably, the system reaches a breaking point. The magma wins. The volcano erupts. It's a simple feedback loop, pressure in versus pressure out. And we've built entire monitoring systems around detecting when that balance is about to tip. But what if that story is incomplete? What if we've been watching a pressure gauge when we should have been studying the entire engine? Because the more scientists analyze what's happening at Axial Seamount, the more they're realizing that they might be looking at something far more complex than a single balloon inflating beneath the seafloor. They might be watching a network of interconnected systems, each with its own thresholds and feedback mechanisms, all influencing each other in ways that don't show up in simple models. The classic volcano model assumes a relatively straightforward geometry. Magma rises into a chamber. The chamber expands. the ground above it deforms measurably. When the deformation reaches a critical value, eruption occurs. It's elegant, testable, and it worked brilliantly for the 2015 eruption. But now, with inflation stalling at levels below previous eruption thresholds, with seismicity patterns that don't quite match what the models predict, scientists are being forced to consider alternatives that make their heads hurt. What if Axial doesn't have one magma chamber, but several, connected by conduits that open and close in response to stress? What if some of the magma that should be inflating the main reservoir is instead migrating laterally into fracture systems we can't directly observe? What if the threshold for eruption isn't a fixed number, but a moving target that depends on factors like the strength of the overlying crust, which might be changing as the volcano heats and cools through repeated cycles? Suddenly, the simple pressure gauge becomes a three-dimensional puzzle with pieces that won't stay in place. This isn't just abstract theorizing. Recent advances in seismic imaging have revealed that volcanic plumbing systems are often far more elaborate than surface deformation alone would suggest. Researchers studying volcanoes in Iceland, Hawaii, and elsewhere have discovered networks of interconnected magma bodies, some actively feeding eruptions, while others remain dormant, some connected by dike intrusions that can transport magma horizontally for miles. The Earth's crust, it turns out, isn't a passive container for magma. It's an active participant in the system, fracturing and healing, channeling and blocking, responding to stress in ways that change the rules of the game. And here's where the January 15th earthquake at Blanco starts to look potentially significant, even if there's no direct mechanical link. The crust beneath the Pacific Northwest isn't a collection of isolated systems operating independently. It's all connected, all responding to the same deeper forces, all part of the massive tectonic engine driven by the Juan de Fuca plate sliding beneath North America. When a magnitude 6.0 quake releases energy at Blanco, it doesn't just shake the immediate area. It sends stress waves propagating through the crust, subtly altering pressure distributions across fault systems and fracture networks for hundreds of miles. Could that stress redistribution affect Axial's magma plumbing? Mainstream science would say the effect, if any, would be minimal. The systems are too far apart, the energy transfer too diffuse. But ask those same scientists if they can rule it out entirely, and you'll get more hedging. Because we're learning that tectonic stress doesn't always behave the way intuition suggests. It can accumulate in unexpected places, migrate through pathways we didn't know existed, trigger responses in systems that seem too distant or too weak to be affected. The Earth is coupled in ways we're only beginning to map. Consider this possibility. What if Axial's inflation stalled, not because magma supply decreased, but because stress in the surrounding crust found alternative pathways? What if the same tectonic forces that drive magmatism beneath the Juan de Fuca ridge are also creating and closing fractures, opening and sealing conduits, redistributing pressure in a three-dimensional network that surface instruments can only glimpse indirectly? In that scenario, the volcano isn't a simple pressure cooker. It's a node in a complex system, and predicting when it erupts requires understanding not just what's happening in the magma chamber, but what's happening in the entire regional stress field. This is where the metaphor of a ticking clock starts to break down. Clocks are predictable. You can measure their mechanism, calculate when the alarm will sound, set your watch by their precision. But geological systems aren't clocks. They're more like biological organisms, complex and adaptive, responding to inputs in ways that depend on history and context and factors we may not even know to measure. The subterranean ticking clock beneath the Pacific Northwest isn't counting down to a predetermined moment. It's evolving, recalibrating, responding to forces on timescales from milliseconds to millions of years. And those forces extend far beyond magma chambers and volcanic conduits. The Juan de Fuca plate, The massive slab of oceanic crust that drives all of this activity isn't a static player in the system. Recent research has revealed that it's actively fragmenting, breaking apart into smaller pieces called microplates, each moving at slightly different rates and directions. This fragmentation is happening right now, in real time, beneath our feet and beneath the Pacific Ocean. And it's changing how stress accumulates, how seismic energy propagates, how magma finds pathways to the surface. The deeper you look into these systems, the more interconnected they become. Magma rising beneath Axial Seamount is ultimately sourced from the mantle, brought to shallow levels by the spreading of the Juan de Fuca Ridge, which is itself driven by plate tectonics, which is powered by heat flow from the Earth's interior, which reflects processes happening thousands of miles below the surface. It's systems within systems within systems, each operating on different timescales, each influencing the others in ways both obvious and subtle. So when scientists talk about the 2026 eruption forecast for Axial, when they hedge their predictions with uncertainty ranges and caveats, they're not being evasive. They're being honest about the limits of current knowledge. They're acknowledging that we can measure many things with exquisite precision, but understanding how all those measurements connect into a predictive framework remains an ongoing challenge. The volcano might erupt this year. It might not. And the thing that determines which outcome occurs might not even be something we're currently monitoring. But here's what's genuinely fascinating, and slightly terrifying if you think about it too hard. If our most comprehensively monitored underwater volcano can still surprise us, if the system can deviate from models that seemed robust just a year ago, what does that say about our ability to predict far more consequential events? What does it say about our understanding of the Cascadia subduction zone, where the entire Juan de Fuca plate is locked against North America, building toward a magnitude 9 earthquake that will dwarf anything Axial can produce? And what if the complexity we're discovering at Axial, the network effects and unexpected couplings and emergent behaviors, are just a preview of what's really happening in the deeper tectonic architecture of the Pacific Northwest? Because that's where this story is actually heading. Let's talk about what happens when inflation stops making sense. For years, the data from Axial Seamount told a consistent story. The volcano would erupt, deflating by several feet as lava drained from the chamber. Then it would begin inflating again, millimeter by millimeter, centimeter by centimeter, the seafloor rising as magma refilled the reservoir. The pattern was so consistent that scientists could literally draw a line on a graph and project when the next eruption would occur. It was volcanic forecasting at its finest, physics-based prediction that actually worked. Then, the line stopped going where it was supposed to go. The inflation curve that had been climbing steadily began to flatten out, hovering around 7 feet of uplift when it should have been pushing toward 8 or 9. And volcanologists found themselves staring at their monitors, wondering if their instruments were malfunctioning, or if the volcano was genuinely doing something unexpected. The instruments were fine. The volcano was misbehaving. Or more accurately, it was behaving exactly according to physical laws we don't yet fully understand. One hypothesis that keeps coming up in research discussions is magma diversion. What if the shallow chamber beneath Axial isn't the only reservoir in play? What if there are deeper magma bodies, or lateral extensions, or dike intrusions branching off into the surrounding crust? In this scenario, magma rising from the mantle might reach a junction point where it can either continue upward into the main chamber or divert into alternative pathways. If those pathways opened up during the current inflation cycle, you'd see exactly what we're seeing. Magma still moving through the system, seismic signals indicating ongoing activity, but surface deformation stalling because some fraction of the magma is going somewhere else. The Earth's crust is not a solid, uniform shell. It's fractured, cracked, shot through with weaknesses from previous intrusions and eruptions and tectonic stresses. When magma pushes against this heterogeneous material, it takes the path of least resistance. Sometimes that path leads directly to the surface. Sometimes it leads sideways, creating dike intrusions that can extend for miles without ever erupting. And sometimes the path changes mid-cycle as new fractures open or old ones seal shut, altering the plumbing system in ways that surface instruments can only infer indirectly. But there's another possibility, one that takes us beyond the volcano itself and into the broader tectonic context. What if stress is migrating into nearby fault systems? The Juan de Fuca Ridge, where Axial sits, is not a quiet, stable feature. It's an active spreading center where new oceanic crust is being created continuously as magma wells up from the mantle. This process generates enormous amounts of stress, pulling the crust apart, creating fracture networks, driving the seismicity that makes the region so active. And that stress doesn't just build up locally. It propagates, redistributes, finds weak points throughout the system. Recent research on plate boundaries has revealed something remarkable and slightly unsettling. The way stress moves through the Earth's crust is far more complex than we once thought. It doesn't just accumulate uniformly and release in predictable earthquakes. It can migrate laterally along fault systems, triggering seismicity hundreds of miles from where it originated. It can load and unload different regions on timescales from days to decades. And it can couple different tectonic processes in ways that seem physically impossible until you actually measure them happening. Think about the Cascadia subduction zone, that massive fault system where the Juan de Fuca plate dives beneath North America. For years, scientists believed it was a relatively simple structure. One plate going down, another plate going up, stress accumulating until a megaquake releases it. But detailed imaging has revealed a far more intricate reality. The subducting plate isn't a single coherent slab. It's fragmenting, breaking apart into microplates that move semi-independently. There are tiers and gaps in the plate, zones where one section is descending faster than another, creating complex stress patterns that don't fit simple models. And here's where things get genuinely speculative, but scientifically intriguing. What if the stress field that's causing Axial's magma chamber to inflate or not inflate is coupled to this broader plate fragmentation process? What if the same forces that are tearing the Juan de Fuca plate apart are also opening and closing fractures in the overlying crust, creating pathways for magma to escape laterally instead of building pressure vertically? It's not a mainstream hypothesis. Most scientists would say the spatial scales are too different, the coupling too weak. But it's the kind of idea that starts to make sense when you zoom out and look at the entire tectonic system as one interconnected machine. Consider the analogy of a windshield. When it cracks, the fracture doesn't propagate randomly. It follows paths of weakness, influenced by stress concentrations, temperature gradients, previous damage. And the fracture can change direction unpredictably based on factors you might not even notice until you analyze it in slow motion. The Earth's crust is similar, except the stresses are measured in millions of pounds per square inch, and the timescales are years instead of milliseconds. When one part of the system fractures or shifts, it changes the stress distribution everywhere else. And those changes can have consequences far from the original event. This is why the January 15th Blanco earthquake matters, even if its direct effect on Axial is probably negligible. It's a marker, a data point, a reminder that the entire region is tectonically active right now. It's like watching warning lights flicker on a dashboard. Any one light might not indicate a critical problem, but when multiple systems start showing anomalies simultaneously, when the volcano is inflating unpredictably and earthquakes are striking nearby, and seismic swarms are increasing, and stress patterns are shifting, you start to wonder if something larger is happening beneath the surface. Historical context makes this even more interesting. Past eruption cycles at Axial followed remarkably consistent patterns. Inflate for roughly 10 to 15 years, erupt, deflate, repeat. The mechanism seemed straightforward. Magma accumulates, pressure builds, threshold is reached, eruption occurs. But what if that pattern only held because the broader tectonic context remained stable during those cycles? What if we're now in a period where the plate configuration is changing, where stress patterns are reorganizing, where the rules that governed previous eruptions no longer apply in quite the same way? Other volcanic systems around the world offer tantalizing hints. The Krafla system in Iceland showed similar behavior during its rifting episode in the 1970s and 80s. Magma intrusions would start, then stall, then resume, creating unpredictable patterns that frustrated forecasters. Eventually, researchers realized they were watching not just a volcanic system, but a plate boundary reorganizing in real time. The magma was opportunistic, taking advantage of fractures created by tectonic spreading, and the timing of eruptions depended on factors beyond simple chamber pressure. Could Axial be in a similar state? Could we be watching a volcanic system adapting to a changing tectonic environment? The Juan de Fuca Ridge is one of the slowest spreading mid-ocean ridges on Earth, creating new crust at a rate of just a few centimeters per year. That slow spreading creates particular types of stress patterns, particular fracture geometries, particular magma supply rates. And if those factors are shifting, even slightly, the volcano's behavior might shift too. There's also the question of fluid migration, a topic that's been getting increasing attention in earthquake science. The Earth's crust isn't dry. It's saturated with water and other fluids that can dramatically affect how rocks deform and fracture. At subduction zones, fluids released from the descending plate are thought to play a crucial role in generating earthquakes and feeding magma chambers. If fluid pathways are changing, if new connections are opening between deep reservoirs and shallow fracture networks, that could alter everything from seismic patterns to magma distribution. All of these hypotheses share a common theme. They suggest that we might be witnessing not just a volcanic cycle, but a system in transition, moving from one configuration to another in ways that don't fit the models built on previous behavior. And if that's true, if the subterranean architecture of the Pacific Northwest is genuinely reorganizing right now, then forecasting becomes exponentially harder. Because you're not predicting the next iteration of a known pattern, you're trying to anticipate the emergence of something new, something the system hasn't done before, at least not during the brief period we've been watching with modern instruments. And that's both scientifically thrilling and, if you live on the coast, slightly terrifying. Let's address the elephant in the room, or more accurately, the speculations swirling around it. When complex geological systems behave unpredictably, and scientists admit uncertainty, that uncertainty becomes fertile ground for theories ranging from the plausible to the absurd. And right now, with Axial Seamount defying expectations and seismic activity elevated across the Pacific Northwest, the theory generators are working overtime. The mainstream concern, the one that keeps geoscientists awake at night, has nothing to do with conspiracies. It's about funding and infrastructure. The Ocean Observatories Initiative, which provides the real-time data streaming from Axial, operates on a budget that's perpetually under scrutiny. These deep-sea cables and sensors are expensive to maintain. They require ship time, specialized equipment, technical expertise, and every budget cycle brings questions about whether the investment is justified, whether we really need continuous monitoring of an underwater volcano that might not erupt for another year, or 5 or 10. Here's the nightmare scenario that researchers whisper about. What if the next critical phase of Axial's inflation, the actual run-up to eruption, coincides with a period when the monitoring network is degraded or offline? What if budget cuts force scientists to reduce the frequency of data collection, and the key precursory signals happen during a gap in coverage? We've built this incredible natural laboratory, one of the few places on Earth where we can watch magma moving in real time, and we're perpetually one budget negotiation away from losing that capability. It's not conspiracy. it's bureaucracy. And it's arguably more frustrating. But let's talk about the speculative ideas, because some of them are genuinely interesting, even if they're not supported by current evidence. One persistent notion is that Axial's unrest could somehow influence the Cascadia subduction zone, potentially triggering or advancing the timeline for a magnitude 9 megaquake. Mainstream seismology says no. The mechanics don't work. Axial sits on the Juan de Fuca Ridge, an extensional tectonic environment where the crust is pulling apart. Cascadia is a compressional environment where one plate is being forced beneath another. The stress regimes are fundamentally different, the spatial separation significant, the coupling mechanisms unclear. But the idea persists because, intuitively, it feels like these systems should interact somehow. They're part of the same plate system. They're driven by the same underlying mantle dynamics. And there are documented cases from other parts of the world where volcanic activity and large earthquakes seem correlated, even if the mechanisms remain debated. Scientists investigating these potential connections usually find that the correlations are either coincidental or involve subtle stress transfers that don't substantially alter earthquake probabilities. But don't substantially alter isn't the same as have absolutely no effect, and that ambiguity leaves room for speculation. Another category of fringe thinking involves unexplained thermal anomalies and gas fluxes from the seafloor. Some researchers, operating at the edges of mainstream acceptance, suggest that heat and chemical signatures detected at various Pacific Northwest seafloor sites don't quite match current volcanic models. They propose alternative scenarios involving unusual rock properties, unexpected connections between magma systems, or even entirely different processes that standard geophysics doesn't account for. These ideas rarely make it into peer-reviewed journals because the evidence is fragmentary and alternative explanations are usually more straightforward. But occasionally, fringe ideas force mainstream science to look more carefully at anomalies it might otherwise dismiss. Conspiracy theories emerge when complex systems produce outcomes that seem too significant to be accidental or purely natural. In the Pacific Northwest, where the population density is high and the seismic hazards are real, any unusual geological activity generates theories about government suppression of information, deliberate triggering of earthquakes, or advanced knowledge of catastrophic events being withheld from the public. These theories are fueled by the fact that governments and institutions sometimes do withhold information, albeit usually for mundane reasons like avoiding panic or waiting for confirmation before making announcements. The reality is almost always more boring than the conspiracy. Scientists aren't sitting on evidence of an imminent megaquake. They're arguing about model parameters and confidence intervals. Officials aren't hiding tsunami projections. They're trying to balance public safety with avoiding false alarms that erode trust. And the geological processes unfolding beneath the Pacific Northwest don't care about human politics or economics or social dynamics. They operate on their own timescales, indifferent to our hopes and fears. But here's a legitimate concern that sometimes gets dismissed as conspiracy thinking, but actually has merit. What happens if critical monitoring infrastructure fails during a crucial period? The seafloor cable network that connects Axial's sensors to shore is a single point of failure. If that cable breaks, if a landslide severs it, if marine life or ocean currents or any number of unpredictable factors damage it, the real-time data stream goes dark. Scientists have backup systems, redundant monitoring from ships and autonomous vehicles, but nothing matches the continuous, high-resolution coverage the cable provides. During the most recent inflation cycle, there have been brief periods when data transmission was interrupted or degraded. These outages were temporary and explained by technical issues, but they highlight the vulnerability of the system. And they raise a question that's uncomfortable to contemplate. If the next eruption happens during a data gap, will we have missed critical precursory signals? Will the forecasting models that depend on continuous monitoring fail because they're missing the key pieces of information? These scenarios are unlikely, but not impossible, and they illustrate why continuous monitoring matters so much. We've gotten used to having real-time data, to watching geological processes unfold live, to feeling like we have a handle on what's happening beneath our feet. But that sense of control is fragile, dependent on technology that operates in one of the harshest environments on Earth, maintained by budgets that fluctuate with political winds. Lose that infrastructure, and we're back to inferring volcanic activity from indirect signals and post-event analysis, the way geologists worked for most of human history. The legitimate concern about information gaps blends into conspiracy thinking when people assume gaps are deliberate rather than accidental. But the underlying anxiety is valid. When something as consequential as a volcanic eruption or a major earthquake depends on systems that could fail for entirely mundane reasons, it's natural to wonder whether we're as prepared as we think we are. And it's natural to fill in the blanks with speculation when official information is incomplete or delayed. So where does this leave us? With a volcano that's behaving unpredictably, monitoring systems that are vulnerable, and a public that's simultaneously informed and anxious about tectonic hazards. Mainstream science continues to do what it does best: collecting data, refining models, hedging predictions with appropriate uncertainty ranges. Fringe theories continue to proliferate in the spaces where data is sparse and explanations are unsatisfying. And in the middle, there's a growing awareness that the systems we're watching are more complex, more interconnected, and more capable of surprise than we'd like to admit. Which brings us to the deeper question: what are those systems actually telling us about the long-term future of the Pacific Northwest? Beneath the Pacific Ocean, in complete darkness under pressures that would turn steel to putty, there are layers of sediment that remember things we've forgotten. These aren't ordinary sediments. They're turbidites, chaotic jumbles of sand and mud and organic material that were deposited rapidly, violently, when something catastrophic happened far above. And when scientists core through these layers, when they bring them up to the surface and analyze their composition and dating, they're reading a history book written in mud. A history of megathrust earthquakes that have shaken Cascadia over and over and over again. The pattern is unmistakable once you know how to read it. Every few hundred years, sometimes more, sometimes less, a massive earthquake ruptures the entire length of the Cascadia subduction zone. The seafloor lurches upward by dozens of feet in some places. The sudden displacement shoves enormous volumes of water aside, generating tsunamis that race across the Pacific. And the shaking destabilizes submarine slopes, triggering underwater landslides that carry sediment from the continental shelf into the deep ocean basins, where it settles into these distinctive turbidite layers. Researchers have identified at least 10 major events in the past 5,000 years, possibly more if you extend the record further back. Each one represents a magnitude 8.5 or larger earthquake, the kind of event that would reshape coastlines, demolish cities, kill thousands or tens of thousands of people if it happened today. And the most recent one occurred on January 26th, 1700, just 326 years ago. We know the exact date because Japanese historical records document a tsunami that struck their coast with no corresponding local earthquake, an orphan tsunami that could only have come from across the Pacific. From Cascadia. 326 years is both a long time and not nearly long enough. The average interval between these megathrust events is somewhere between 300 and 600 years, with enormous variability, which means we could be overdue, or we could have centuries left to wait, and the geological record can't tell us which. It can only tell us that it will happen again, that the process driving these earthquakes is ongoing, and that the energy currently locked in the Cascadia fault is building toward another release. Now let's be very clear about something. Axial Seamount has nothing to do with Cascadia megathrust earthquakes. They're different systems, different mechanisms, different timescales. A volcanic eruption 300 miles offshore won't trigger a magnitude 9 subduction zone earthquake. The physics don't work that way. But, and this is a significant but, both systems are part of the same tectonic environment, driven by the same plate motions, responding to the same deep mantle processes. And understanding how one part of that environment behaves can offer insights into how the other parts might behave. The turbidite record doesn't just tell us when megaquakes happened. It tells us about variability, about how these events cluster in time, about how the system behaves over millennia rather than decades. And what that record shows is a system that's anything but regular. Sometimes megaquakes come in clusters, multiple events over a few centuries. Sometimes there are long, quiet periods, gaps of 1,000 years or more. The Earth doesn't run on a clock. It runs on physics that we're still trying to fully understand. The connection to axial, tenuous as it may be, comes from thinking about stress and how it distributes through tectonic systems. The Juan de Fuca plate is descending beneath North America at a rate of about 3 to 4 centimeters per year. That motion is steady, inexorable, driven by forces that make continental drift look like geological sleepwalking. And as the plate descends, it bends, fractures, releases fluids, and builds up enormous strain where it's locked against the overriding North American plate. That strain will eventually be released in a megaquake. The only question is when. Some researchers have speculated, controversially, that volcanic activity along the Juan de Fuca ridge could influence stress states in the subduction zone. The idea is that if magma intrusion or plate spreading rates change, even slightly, it could alter the forces acting on the locked portion of the fault. Most seismologists are skeptical. The distances are too great, the coupling mechanisms too weak, the magnitude of any effect too small to meaningfully change earthquake probabilities. But the idea persists because we don't have perfect knowledge of how all these systems interact. What we do know with confidence is that the Pacific Northwest sits atop one of the most dangerous seismic zones in North America. The turbidite record proves that massive earthquakes have happened repeatedly in the geologically recent past. The GPS measurements show that strain is currently accumulating across the locked fault zone. The paleoseismic evidence from coastal marshes, where ghost forests of trees killed by sudden subsidence mark past events, confirms that this isn't theoretical. And the historical precedent from other subduction zones around the world, from Japan to Chile to Sumatra, shows us exactly what a magnitude 9 earthquake can do to a modern society. The 1960 Chile earthquake, magnitude 9.5, the largest ever recorded, killed thousands and caused tsunamis that propagated across the entire Pacific Ocean. The 2004 Sumatra earthquake, magnitude 9.1, generated tsunamis that killed over 200,000 people in multiple countries. The 2011 Japan earthquake, magnitude 9.1, despite occurring in one of the most earthquake-prepared nations on Earth, killed nearly 20,000 people and triggered the Fukushima nuclear disaster. These are not ancient history. These are events within living memory, and they're the kind of events that Cascadia is fully capable of producing. So when scientists monitor axial seamount inflation cycles and watch seismicity patterns across the Pacific Northwest, they're not just studying individual phenomena. They're trying to understand a system, a region, a tectonic environment that has proven itself capable of catastrophic violence. And every data point, every anomaly, every unexpected behavior in any part of that system is potentially informative about how the whole thing works. The turbidite layers in the deep ocean don't care about human timescales, or political boundaries, or insurance actuarial tables. They record what happens when enormous amounts of energy, accumulated over centuries, are released in seconds. And they tell us that this process has happened at least 10 times in the past 5,000 years, which means it's not a matter of if, but when. The next Cascadia megaquake is coming. The coastal communities built since 1700 have never experienced one. And when it arrives, it will make every earthquake in recorded Pacific Northwest history look like a minor tremor by comparison. The question that keeps geophysicists up at night isn't whether it will happen. The question is whether we'll get any warning. Modern subduction zones sometimes show precursory signals before major earthquakes. Slow slip events, changes in seismicity patterns, anomalies in GPS measurements. Sometimes they don't. The 2011 Japan earthquake was preceded by foreshocks, giving at least a brief warning. The 2004 Sumatra earthquake struck with almost no precursors, and we have no idea which scenario Cascadia will follow. This is where monitoring matters, not just at Axial, but across the entire offshore region. Every seismometer, every GPS station, every ocean bottom pressure sensor is part of a network designed to detect the earliest possible signs that the locked fault might be starting to move. Because if we get days of warning, we can evacuate coastal areas, move people to higher ground, prepare emergency response. If we get hours, we can send alerts, activate sirens, give people time to seek shelter. If we get minutes, all we can do is hope the building codes hold, and that people remember to duck, cover, and hold on. Here's something that would have seemed like science fiction even 20 years ago. Scientists have now watched, in real time, as a tectonic plate tears itself apart. Not in geological time, not inferred from ancient rocks, but actually observed with modern instruments as it's happening right now, beneath our feet and beneath the Pacific Ocean. The Juan de Fuca plate, that slab of oceanic crust that's been driving so much of the Pacific Northwest's geological drama, is fragmenting. It's breaking into smaller pieces, called microplates, each moving semi-independently, each creating its own stress patterns and earthquake risks. This discovery comes from combining multiple imaging techniques. Seismic tomography that maps the Earth's interior like a medical CT scan, GPS measurements that track surface motions to millimeter precision, ocean floor magnetism studies that reveal the history of seafloor spreading, and computer models that simulate how tectonic plates deform under stress. And what all these techniques reveal is that the simple model of tectonic plates as rigid slabs moving around on the Earth's surface is exactly that. Simple, useful, explanatory, but incomplete. The reality is far more dynamic. Plates aren't rigid. They bend, flex, crack, and fragment in response to the forces acting on them. And the Juan de Fuca plate, squeezed between the massive Pacific plate to the west and North America to the east, is under particular stress. It's relatively small as oceanic plates go, just a remnant of a much larger plate that once spanned the entire eastern Pacific. And as it continues to be subducted beneath North America, as it bends and descends into the mantle, it's starting to break up. What does this mean for places like Axial Seamount? Potentially a lot. Submarine volcanoes along mid-ocean ridges are fed by mantle upwelling, by hot material rising from depth to fill the gap created as plates pull apart. If the plate geometry is changing, if new fractures are opening and old ones are sealing, the pathways that magma follows to reach the surface might also be changing. This could explain why Axial's inflation cycles are becoming less predictable, why the volcano seems to be following a different script than previous eruptions. And it might explain something even more fundamental: why the Pacific Northwest is such a tectonically complex region in the first place. Most subduction zones around the world show more regular patterns of seismic activity. Earthquakes happen, yes, but they follow recognizable cycles linked to strain accumulation and release. Cascadia has always been a bit different, with its unusually long intervals between megaquakes, its mixture of locked and creeping sections, its spatial variability in behavior. If the underlying plate is fragmenting, that could introduce complexity that makes the system harder to predict. This evolution of tectonic understanding represents a broader shift in Earth sciences. We've moved from a static view of the planet, where continents and ocean basins were permanent features, to a dynamic view where everything is moving but predictably, to an even more sophisticated view where the motion itself evolves over time. Plates don't just move, they change as they move. They adapt to stresses. They reorganize. And those reorganizations can happen on timescales short enough to matter for human societies. The implications extend beyond earthquakes and volcanoes. As plates fragment and reconfigure, they affect mantle circulation patterns, which affect heat flow, which affects everything from the depth of earthquakes to the chemistry of volcanic eruptions, to the long-term evolution of Earth's magnetic field. It's all connected, all part of a planetary system that's been operating for 4.5 billion years and shows no sign of stopping. Consider what this means for hazard assessment. Traditional approaches assume that the past is a good guide to the future. If megaquakes happened every 400 years on average in the past, we can estimate future probabilities based on that rate. But if the underlying plate configuration is changing, if stress patterns are reorganizing, then past behavior might not perfectly predict future behavior. We might be entering a new phase of Cascadia's evolution, one where the rules are subtly different from what the turbidite record suggests. This isn't cause for alarm so much as recognition that uncertainty is inherent to the system. We can measure current conditions with extraordinary precision. We can model physical processes with sophisticated mathematics. We can learn from the geological record and from global analogs. But we can't eliminate the fundamental uncertainty that comes from studying a complex adaptive system that's actively evolving, and honestly acknowledging that uncertainty is more scientifically rigorous than pretending to certainties we don't possess. The fragmentation of the Juan de Fuca plate is just one example of Earth's ongoing tectonic activity. Around the world, plates are colliding, separating, sliding past each other, subducting, fragmenting, reorganizing. The Pacific plate is moving northwest at 8 to 9 centimeters per year, creating the Hawaiian Islands through hotspot volcanism and driving subduction zones from Alaska to New Zealand. The African continent is slowly rifting apart along the East African Rift, potentially creating a new ocean basin over the next tens of millions of years. India continues to plow into Asia, pushing up the Himalayas at a rate of about 5 millimeters per year. But it's a privileged moment. For the first time in Earth's history, a species has emerged that can watch these processes in real time, understand them quantitatively, and use that understanding to protect itself from the hazards they create. We can forecast volcanic eruptions with increasing accuracy. We can map fault zones and estimate their earthquake potential. We can model tsunami propagation and design early warning systems. We can't prevent any of these events, but we can prepare for them in ways that previous generations couldn't imagine. The next decade will likely reveal even more about how tectonic systems evolve. New satellite missions will provide better constraints on crustal deformation. Expanded seismic networks will image the Earth's interior with higher resolution. Improved computer models will simulate tectonic processes more realistically. And every new dataset, every refined model, every unexpected observation will force us to update our understanding, to recognize new complexities, to acknowledge both what we know and what we still don't know. This is Earth alive, not static, not predictable in every detail, but dynamic and evolving. The Juan de Fuca plate is fragmenting right now. Axial Seamount is inflating toward an eventual eruption right now. Strain is accumulating across the locked Cascadia megathrust right now. And somewhere in the Pacific Northwest, maybe decades from now, maybe tomorrow, the accumulated stress will exceed the friction holding it in place, and the ground will shake with a violence that will make headlines around the world. When that happens, whether it's a volcanic eruption that researchers have been monitoring, or a megaquake that catches everyone by surprise, it won't be a failure of science. It will be Earth doing what Earth has always done, operating according to physical laws that we understand increasingly well, but that still contain elements of irreducible uncertainty. And our job as the species that's figured out how to watch these processes unfold is to keep watching, keep learning, keep preparing, and keep marveling at the fact that we live on a planet dynamic enough to still surprise us after all these years of study. The subterranean forces beneath the Pacific Northwest aren't ticking down to a predetermined moment. They're evolving, adapting, reorganizing in response to forces operating on scales from kilometers to thousands of kilometers, from seconds to millions of years. And every strange inflation curve, every unexpected earthquake, every fragmenting plate and migrating microplate is part of that story. A story that's been unfolding since long before humans existed and will continue long after we're gone, but that we're privileged to witness and understand, if only imperfectly, for this brief moment in geological time.